Good morning, sir. Today we are excited to present our visual environmental navigator system project, which is an assistive technology designed to help visually impaired individual gain greater independence and environmental awareness. According to the World Health Organization, approximately 285 million people worldwide are visually impaired, with 39 million classified as fully blind. Traditional navigation aids like white canes and guide dogs provide limited information about the surroundings, creating significant challenges for blind individuals trying to navigate complex environment. So our solution leverages edge and fog computing to create a system that captures visual information, processes it using advanced AI, and provides real-time audio description to users, effectively seeing and explaining the environment for them. Now, what is our system overview and edge computing architecture? What we have implemented here. So, going on that, the visual environment navigator employs a distributed computing architecture with both edge and fog computing components working together seamlessly. At the edge level, we have implemented an ESP32 microcontroller paired with an ESP cam module that captures real-time video feed from the user perspective. This edge device handles several critical functions. First, image capture and pre-processing at 5 to 10 frames per second, secure data transmission to a fog processing layer, receiving process description from the server, and the text to speech conversion using Google text to speech converter API. Audio output is managed via MAX 98375A amplifier and speaker. Now, this edge computing approach provides several advantages for our application by performing initial processing and data management at the device level. We significantly reduce latency and bandwidth requirements. So the ESP32 was selected specifically for its excellent power efficiency and robust wireless connectivity options, making it ideal for this project. Now, hardware implementation details. So I will show you the hardware details in this. So these are like that. So here you can see first we have used the ESP32 microcontroller to process the data at a fog nodes. We used the breadboard also. Now this is the ESP32 cam module to capture the images and send it to the user, send it to the API to the server to process it and generate the text. This is an amplifier for our speaker. This is Max 9857A amplifier, which amplifies the images and send it to the server. This is a speaker which will be working after we converted the text to we have processed the image and converted into the text. So now, so this is the overall hardware, and we are going to implement this as it is. Now, okay. So if we go in specific details, we have also implemented a 4 ohm speaker rated at 3 watts handles, which handles the audio output, and a 3.7 LiPo battery with 2500 mAh capacity powers the entire system. So the edge processing pipeline begins with image capture where the ESP32 instructs the ESP cam to take a photo at regular intervals. These images are then compressed to approximately 50 kb to optimize transmission. The ESP32 establishes a secure WebSocket connection to a fog server, transmitting the captured image data efficiently. Now, if we come to a proper edge-to-edge communication system, so it works like that. It affects our system, affects our life in a very helpful manner. Whereas it is also gives a critical aspect of a system in the seamless communication between the edge device and fog server. We have implemented a lightweight messaging protocol that minimizes overhead while ensuring reliable data transfer. The ESP and this in this the ESP32 maintains a persistent connection to the fog server, in which sending images and receiving text description through this optimized channel. One of the key challenges that we encountered was managing the power consumption while maintaining the responsive performance. By implementing adaptive sampling rates that adjust based on detected environmental changes and user movement, we have achieved a balance between responsiveness and battery life. Now I will hand over to my colleague.
Thank you, Aditya. As now we transition from the edge to the fog layer of our system, I'll now explain how we process the visual data and generate meaningful descriptions for the blind users. Now, further, I will show the code. The system utilizes two ESP32 microcontrollers with specific roles. These are the two which are being used. ESP32 CAM. It functions as the visual input device and captures images when requested. The other one is ESP32 TTL, functions as the output audio device and receives the text and converts it into the speech. Now, there's a for loop over here. The script now begins to establish a connection with the ESP32 CAM through multiple HTTP requests. The primarily sequence of requests serve as the warm-up that ensures that the camera is ready and responsive before capturing the actual image. The ESP32's CAM web server typically needs these initial connections to establish the camera's module operation. After the warm-up, we go ahead to do the response. This part is the response. In the response, once we have successfully got a status code of 200, the ESP32 CAM responds that the image data is in binary format. Further, now we go to the try block. In this try block, once the image has been retrieved, the script processes it for transmission to the AI service. The script uses the Python library, imaging library, that is an open source binary image data stored in memory. This allows for verification that the image is valid and properly formatted. Next, the image is converted into a base64 encoded string, which is a text representation of binary data that can be safely transmitted in JSON. Now, this is the conversion in binary data. This process mainly involves loading into a memory buffer, saving the image to the buffer in JPEG format, converting the buffer contents to base64, decoding the base64 bytes to UTF-8 string. The resulting 64-bit string then represents the image of in a format that can be embedded in a data URI scheme, which allows the image to be included directly in an API request. Now here we come across the main model, which is the AI-powered image analysis. This is the heart of our system, which is the API call to the Open Router service, which provides access to the Qwen 2.5 Visual Language Model. The complex request includes the authentication with the Open Router API, the specificities of the Qwen 2.5 VL model. It is a powerful multimodal AI model capable of understanding images. Provides a system image that defines how the AI must describe images. It also includes a user message with both text as well as base64 encoded image. The system prompts a specific design for assistive technology needs, instructing the model to keep descriptive descriptions very concise. These constraints are intentional so that we can design it for blind users to be very clear, and immediate information about their surroundings without overwhelming them is provided to them. Now we go to the processing of the response, which is almost the last part of the code. Once the AI generates the description, the script then extracts it and ensures that 200 character limit is only limited to it. And this truncation with the ellipse preserves the most important information while maintaining the character limit requirements for the ESP32 text-to-speech system. The final text-to-speech output is the description which is sent to the ESP32 device for the audio output. The text-to-speech ESP32 function is imported from a custom module called as the sendText, which handles the communication to the ESP32 TTL device. Okay, so this is the hardware system. Now this is also connected to a wired earphone, which is being used by Aditya. Now he will be able to hear the audio whichever is generated by this. Now he can point it towards the device, towards the environment, and this will give a description. So if I run the script over here, you'll have to wait for a couple of seconds, and here you will be able to obtain and see the description of the environment, and he will also be able to hear about the audio. So it will take a little time to process. This is being given now that since it is an API call which is going to Qwen AI, the time it takes is little much. Yeah, so over here you can see on a table a blue bottle with a white cap sits next to a black device with an orange light, and a white tag hangs from this device, and a shadow of a person stands to its left. Now, this is a very clear description of what is actually over there. So, this is going to be how a blind person is going to be assisted, and this audio will be heard by the user. So now that we have done the demonstration, let me talk about the advantages of our system. Uh, First of all, low latency. Processing at the network edge means faster response time compared to cloud-based solution, especially for real-time navigation assistance. Reliability. A system can maintain basic functionality even during connectivity interruption, as the ESP32 can fall back to local processing for critical functions. Privacy preservation. Sensitive visual data is processed locally within our fog infrastructure rather than being transmitted to distant cloud servers. Scalability. Our architecture allows easy deployment of multiple edge devices connecting to a single fog server, making this solution cost effective for institutional implementations. Power efficiency. By distributing processes between the edge and the fog layer, we optimize battery life by maintaining high quality output. There are practical applications and future implementations, also enhancements of this project. Our visual environment navigator provides immediate practical benefits for visually impaired users in various scenarios. Indoor navigation in unfamiliar buildings, identification of objects and obstacles in a path, reading of signs, products and displays, recognition of people and social cues, also enhance situational awareness in dynamic environments. Future enhancements will include integration of geological data to provide contextual information, implementing object memory to sophisticated understanding of the user's preferences through edge-based learning. We are also exploring the potential to create a mesh network of these devices that could, share environmental data through fog nodes, creating a more comprehensive understanding of spaces frequently navigated by visually impaired individuals. Now, this concludes our demonstration of the visual environment navigator. We believe that this project showcases how thoughtfully implemented edge and fog computing architectures can create meaningful solutions for important accessibility challenges. Thank you for your attention, and we are happy to present this.